and entropy. What we're looking at is that spontaneity needs both enthalpy and entropy in order for us to understand it. So for any given system, any given process, enthalpy can either tend towards spontaneity or non-spontaneity. Exothermic processes tend to be spontaneous. Endothermic processes tend to be non-spontaneous. When we're looking at entropy, for this particular system and this particular process, increasing entropy tends to be spontaneous. Decreasing entropy tends to be non-spontaneous. All right. Now, just to be clear, for any given system, an endothermic process can still be spontaneous. Remember, Epsom salts. Epsom salts dissolving in water, right? That's still a spontaneous process. You drop them in water, they will dissolve, even though that's an endothermic process. Decreasing entropy can still be spontaneous. Hydrogen and oxygen reacting to make water. That is a decrease in entropy. You have 3 moles of gas going to 2 moles of gas. That's still a spontaneous process. Okay. Excuse me. That's why you need both of these. Okay. You have to have both enthalpy and entropy in order to understand whether a process is spontaneous. Okay. So, when they cooperate, it will always be spontaneous. An exothermic process that increases entropy. Okay. For example, burning butane. Okay. Burning almost any organic compound is going to both increase entropy and be exothermic. Okay. Therefore, that will always be spontaneous. An endothermic process that decreases entropy is pretty much never going to be spontaneous. Okay. When things get difficult is when they are acting in opposite directions. Okay. An endothermic process that increases entropy or an exothermic process that decreases entropy. Okay. Remember, endothermic tends to be non-spontaneous, but increasing entropy tends to be spontaneous. Exothermic tends to be spontaneous, but decreasing entropy tends to be non-spontaneous. They're acting in opposite directions. So when you have a situation like that, it might be spontaneous, it might not. That is going to depend on temperature. So, the way we figure this out is by looking at the entropy of the universe. Not the entropy of the process, but the entropy of the universe. The entropy of the universe always increases. So delta S of the universe is always going to be positive. Okay? That's the second law of thermodynamics. Entropy of the universe always increases. Now, system plus surroundings is universe, remember? The system is what we care about. The surroundings is literally everything else in the universe. So the change in entropy of the universe is the change in entropy of the system plus the change in entropy of the surroundings. But remember, in this case, it's not equal to 0. For energy, that is equal to 0. But for entropy, it is not. Now, the change in entropy of the system is measurable. We can measure that. The change in entropy of the surroundings is also measurable. Okay? We can measure both of those by various means, by various ways. Now, delta S of the surroundings is the heat change of the surroundings divided by the temperature of the surroundings. And the heat change of the surroundings is just equal and opposite the heat change of the system. And temperature of the surroundings we can assume is constant because the surroundings are big. So, delta S of the surroundings is negative Q of the system divided by T is equal to negative delta H divided by T. So the change in the entropy of the universe is equal to the change in entropy of the system, minus delta H of the system divided by T. That is a big deal. We have just managed to define the change in entropy of the universe solely in terms of the system. We no longer need to measure the entire universe. We just have to measure the system. Okay. So, entropy is the more important thing. But this was developed in the 19th century, and people had a better grasp on enthalpy, better grasp on energy. They looked on entropy with suspicion. They didn't like the whole randomness and disorder and freedom thing. They didn't care. They didn't like freedom. They wanted everything in its place. So, what we do is they rearranged, is what they did. So multiply both sides by negative temperature. So we have delta S minus delta H over T. Multiply both sides by negative T. Okay. That gets you negative T delta S is equal to delta H minus T delta S. Okay, just a quick bit of algebra. Temperature times entropy, state function, so still state function. So what they did is they gave it a new name, a new state function. And they called it Gibbs free energy. That is to say, the energy in the system that is free to do work. So, free energy. And it's named after a dude named Josiah Willard Gibbs. So, negative T delta S of the universe is delta G of the system. Delta G, Gibbs free energy, or the change in Gibbs free energy, is equal to delta H minus T delta S. Or, at standard conditions, delta G standard is equal to delta H standard minus T delta S standard. This is an important function. You need to remember this. Okay? Delta G is equal to delta H minus T delta S. Do not forget. It was named after Josiah Willard Gibbs, as I said. A dude who published his work on this stuff in the Connecticut Review of Letters, which wasn't even read in Connecticut. And, you know, just looking this guy up on Wikipedia, I found this series of pictures, and I just love Josiah Willard Gibbs. From this nebbishy little dude with, you know, just this ridiculous bow tie and this absurd hair, to a guy in his 30s. He's starting to rock a good beard, but his hair is still ridiculous. To bam, silver fox. He's rocking it. Got it going on. Gibbs, later years, knew what he was doing. All right. But the real point is this right here. Delta G is equal to delta H minus T delta S. So let's look at delta G, delta H minus T delta S. Seriously, that hair. All right. So Gibbs free energy. This is the energy, the potential energy within a system that can be made to do work. Now, for a spontaneous process, second law of thermodynamics, the entropy of the universe will always increase for a spontaneous process. So delta S of the universe will always increase, and delta G of the system is negative T delta S of the universe. Okay? So delta G will decrease for a spontaneous process. It will increase for a non-spontaneous process. And if it's equal to 0, then your system is at equilibrium. Okay? So negative delta G means spontaneous. Positive delta G means non-spontaneous. 0 means equilibrium. The actual magnitude of the number is a little bit less important, at least right now. What really matters is the sign. Negative means spontaneous, positive means non-spontaneous, 0 means equilibrium. So one way to think about this: enthalpy, H, versus entropy, S. Enthalpy is the drive of the universe toward order. Entropy is the drive of the universe toward freedom. Okay? Enthalpy loves snuggles. Entropy loves freedom. The reason this is important is because they dominate at different temperature values. Enthalpy dominates at low temperature. Entropy dominates at high temperature. Okay. So cold weather is snuggle weather. Hot weather, you don't snuggle. Okay. You don't snuggle. I mean, you might still, you just don't snuggle because it's hot. Okay. So enthalpy, delta H, dominates at low temperatures. Entropy, delta S, dominates at high temperatures. So that gives us our 4 possibilities. Enthalpy in the column, entropy in the row over here. All right. So positive enthalpy means an endothermic process. A negative enthalpy, so this is H in the columns, negative enthalpy means exothermic. Positive entropy means an increase in entropy for the system. Negative means a decrease in entropy for the system. Okay. So remember, endothermic tends to be non-spontaneous. Exothermic tends to be spontaneous. Increase in entropy tends to be spontaneous. Decrease in entropy tends to be non-spontaneous. Okay. So they cooperate in these 2 quadrants here. Okay. An exothermic process that increases entropy is always going to be spontaneous. An endothermic process with a decrease in entropy will never be spontaneous. Okay. It's always going to be non-spontaneous. These are the 2 quadrants where they work in opposite directions. Okay. If it's an endothermic process, endothermic tends toward non-spontaneous, but an increase in entropy tends to be spontaneous. Okay. And remember, entropy dominates at high temperatures. Enthalpy dominates at low temperatures. So if enthalpy says no, entropy says yes, then it will be spontaneous at high temperatures. Conversely, if you have an exothermic process, exothermic tends towards spontaneous. With a decrease in entropy, decreasing entropy tends to be non-spontaneous. Enthalpy dominates at low temperatures. Entropy dominates at high temperatures. Therefore, if enthalpy says yes and entropy says no, it will be spontaneous at low temperatures. So, something that an endothermic process, positive enthalpy, that increases entropy, well, that would be something like boiling water. Boiling water, you have to put energy in. It is an endothermic process, but you're going from a liquid to a gas. Liquid is lower entropy than a gas. Gas is higher entropy, more freedom. The particles of the gas are free to move. So boiling water is going to be spontaneous at high temperatures. It's going to be non-spontaneous at low temperatures. Conversely, an exothermic process that decreases entropy, well, that's something like freezing. Okay, freezing is an exothermic process. It's releasing energy into the surroundings. It's cooling down. It's getting colder. And it decreases entropy, going from a liquid to a solid. Liquid is more free than a solid, so it's a decrease in entropy going from liquid to solid. Thus, an exothermic process that decreases entropy, like freezing, is going to be spontaneous at low temperatures. All right. So there are two ways for us to calculate Gibbs free energy. One is by, for any given process, we can calculate Gibbs free energy, or the change in Gibbs free energy, by calculating the change in enthalpy for the process, calculating the change in entropy for the process, then delta G is equal to delta H minus T delta S. The other way is we look up the numbers on a table, just like we do for delta H and delta S. Excuse me. And in that case, delta G is products minus reactants, just like delta H and delta S are. So, first, what is the change in Gibbs free energy for boiling water at various temperatures? The change in enthalpy for boiling water is 40.660 kilojoules per mole. So that's delta H for that process. The change in the change in entropy for the process is the change in entropy from liquid water to gaseous water. So delta S is gas minus liquid. So let's go ahead and bring up our calculator. 232.57 minus 123.55. The change in entropy for that process is 109.02 joules per Kelvin. It's an increase in entropy. So, increase in entropy, 109.02, and an endothermic process. And then the change in Gibbs free energy is delta H minus T delta S. Now, like I said yesterday, you absolutely must be careful about your units. Okay, enthalpy is recorded in kilojoules. Entropy is in joules per Kelvin. You need to get those units to match, otherwise when you do the delta H minus T delta S, your number will be wrong. Okay, so let's go ahead and convert from joules per Kelvin to kilojoules per Kelvin. In other words, let's go ahead and divide by 1,000. Oops, come on. So the change in entropy is 0.10902 kilojoules per Kelvin. So delta H is 40.660 minus our change in entropy, 0.10902, multiplied by the temperature. Now, I asked about 3 different temperatures: 90 degrees, 100 degrees, and 110 degrees. When you are doing this kind of math, it absolutely, positively has to be in Kelvin. It cannot stay in degrees Celsius. So remember, to convert from Celsius to Kelvin, you add 273.15. So 0 degrees Celsius is 273.15 Kelvin. 100 degrees Celsius is 373.15 Kelvin. Okay. So 90 degrees Celsius is going to be 363.15 Kelvin. Okay. So that is the math, okay? Might be a little bit hard for you to see. I don't know how the YouTube is looking there. Clear enough, I guess. So our delta H, 40.66, minus T delta S. T is the 363.15, 90 degrees Celsius in Kelvin. Our delta S was the 0.10902, converted to kilojoules. So at 90 degrees Celsius, delta G is positive 1.07. Remember, the magnitude, the size of delta G doesn't matter nearly as much as the sign. Delta G is positive. Positive delta G means non-spontaneous. And that's exactly what you would expect. At 90 degrees Celsius, water doesn't boil. You would expect a zero or a positive delta G. You would expect it to be non-spontaneous. So let's look at it for 100 degrees Celsius. At 100 degrees Celsius, it is 40.66 minus 373.15. That is 100 degrees Celsius converted to Kelvin times 0.10902, the change in entropy, delta S, gives us negative 0.0208. Well, that's just a rounding error. At 100 degrees Celsius, it should be 0. Delta G should be 0. The fact that it's not is just because we're not working with really, really great numbers here. Okay. We should expect the boiling of water to have a delta G of 0 at 100 degrees Celsius. And at 110 degrees Celsius, 40.66 minus 383.15 times 0.10902 gives us a negative delta G. You would expect the boiling of water to be very spontaneous at 110 degrees Celsius. Okay. So again, it's not so much about the magnitude as it is about the sign, positive or negative. All right. So that's one way to calculate delta G, okay? The change in Gibbs free energy. You find delta H for the process. In this case, it was just given to you. Delta H was this. But remember, you can calculate delta H by products minus reactants. Okay. You are more likely to be given a chemical reaction, and then you just multiply you take the delta H of formation, basically, for all the products, the delta H of formation for the reactants, multiply everything by the coefficients, and then products minus reactants, right? And then you do the same thing for entropy. Products minus reactants. That gives you delta H and delta S. And then Gibbs free energy is delta H minus T delta S. You'd have to be given the temperature. Otherwise, it wouldn't work. So the other way is if you are given delta G for a process, or delta G of formation for all the stuff in the process, you can just do products minus reactants directly for delta G. So, for example, we have copper reacting with hydrochloric acid to make copper chloride and hydrogen gas. Is this reaction spontaneous? Okay. Well, here we have the entropy, or sorry, the change in Gibbs free energy for all the substances involved, except for hydrogen. Why is that? Just like enthalpy, the change in Gibbs free energy for the formation of an element in its natural state is 0. So delta G of formation, delta H of formation for hydrogen, for any element, is going to be 0. Not for the other things, but for the elements. So copper and hydrogen, they're both elements in their native state. Therefore, delta G is 0. So once again, we bring up the calculator. So on the product side, parentheses, we have 1 mole of the copper 2 plus ion, so 65.5 plus, and then we have 2 moles of the chloride, 2 times negative, times 131, oops, 131.2 negative, close parentheses. So that is the products, negative 196.9 minus, on our product side, we have 2 times, for the HCl, 131.2 negative, close parentheses, giving us positive 65.5. Okay, so once again, it's going to be a little hard to see, but reactants or products minus reactants. Our products are the 2 ions, the copper and the chloride, and our reactants is the HCl. Giving us a change in Gibbs free energy for this particular reaction of positive 65.5. Once again, the size of the number is less important than the sign. It is a positive number, therefore non-spontaneous. An increase in Gibbs free energy means a non-spontaneous reaction. So if you were to drop a copper penny into hydrochloric acid, it would not react. And that is what we see. Copper does not react with acid. So those are the 2 ways of calculating Gibbs free energy. Okay. You calculate delta H and delta S for the process, for the reaction. Doing products minus reactants for delta H, you do products minus reactants for delta S, and then delta H minus D delta S. Okay. That's a lot of work. It's annoying. Plenty of opportunities to make mistakes, but easy enough to do. Or you can be given the change in Gibbs free energy directly for all the substances involved, and then it's products minus reactants in the exact same way. Okay. So going back to an earlier set of slides, let's see if I can find it. Let's see. Was it here? It was not. Okay, so let's, it was probably here. Yes. Okay. So the textbook will have a set of tables that look a lot like this, just a whole big list of substances, and then you'll have the enthalpy of formation, change in Gibbs free energy, and the entropy for the substance. Okay. And, you know, you can calculate delta H for a process by doing products minus reactants. You can find delta S for the process doing products minus reactants. And you can find delta G by doing products minus reactants. Lots and lots of tables all like this. And notice that for an element in its native state, 0 enthalpy, 0 Gibbs free energy, but not 0 entropy. Okay. So try to remember that as well. And with that, we have finished chapter 8. Okay. So plenty of practice in the textbook. Do those end of chapter problems. I know that the section 3 retest is tonight, so good luck with that. Then we have the test on this for Monday. I will be checking my email and the Discord assiduously all weekend to answer your questions on those. And speaking of questions, I will now sit and wait for about 30 seconds to see if you have any questions. You move 16 times, what do you get? Another day older and deeper in debt. I do not know that, Megan. I do not know where to find that date and time. I suspect they're still working on that and that they'll post it early next week. Or at least I hope so. All right. And that appears to be the only question. So I will bid you adieu.